let me summarize what we have done up to now. So we had a field K, and we said that alpha was algebraic over K if it was a root of a polynomial. With coefficients from K. We said that L was algebraic over K if any alpha in L was algebraic over K. We said that F was finite over K if it was a finite dimensional K vector space. We have seen that finite implies algebraic. We have seen that in fact it is equivalent to algebraic and generated by a finite number of elements. So say finitely generated. And we have seen that if we generate our L by a single element alpha, we have seen that the degree of K of alpha over K was equal to the degree of the minimal polynomial of alpha over K. So, given some algebraic element over K, a root of some polynomial, it is important to be able to decide whether this is the minimal polynomial of alpha over K. That is to say, it is important to have some irreducibility criteria. And this is something you probably already know, but since it's so important, I would like to remind a couple of things about this. So, how to decide that a polynomial is irreducible over K? Well, in our example, we had a very simple polynomial. So, x cubed minus 2 was irreducible over Q, since it's a cubic polynomial. So if it was not irreducible, it would have a root in Q. So this is easy since the degree is equal to 3 and there is no root. But, well, if you ask the question whether x to the power 100 minus 2 is irreducible or not, this is already not so simple, right? Well, this is irreducible. And here are a couple of facts which help to see this easily. So, fact 1. This is usually called the Gauss lemma. If P decomposes non-trivially, well, by this I mean is a product of two factors of strictly smaller degree, that is, P is Q times R, where the degree of Q and the degree of R are both less than the degree of P, or the same is to say that they are both strictly positive. So if this is the case over Q, then it is also the case over Z. Well, of course, I have to say that I am considering a polynomial with integral coefficients. So if such a polynomial decomposes non-trivially over Q, then it also decomposes over Z. Well, let me give a proof. So let over Q, write P is equal to Q times R. They are not integral, but of course you can multiply them by a common denominator and they become integral. So let's say MQ is equal to Q1 in Z, and NR is equal to R1 in Z. Then we have MNP is equal to Q1 R1 over Z. Then take P, which divides Mn. Then modulo P. We have 0 is equal to Q1 bar R1 bar, where bar denotes the reduction modulo P, right? Well, but we are over Z modulo PZ, which is a field. So modulo P means over Fp, right? This is a field. So we have Q1 bar or R1 bar is 0. This means that P divides all coefficients either of Q1 or of R1. So P divides all coefficients C of Q1. And then we can write Mn over P times our big P is Q2 times R1 in Z of X, and here Q2 is of course Q1 divided by P. Continuing in this way, we arrive at P is equal to, I don't know, Q L R S in Z of X. Okay, and fact 2. Let me not prove it in full generality. Let me just show this on an example and then formulate maybe a general criterion. Fact 2 is Eisenstein criterion. Well, how to show that x to the power 100 minus 2 is irreducible over z? This is very easy. We reduce modulo 2. And so if x to the power 100 minus 2 decomposes non-trivially as q times r, then modulo 2 x to the power 100 is q bar times r bar in f2 of x. Yes, but this means that q bar and r bar are of the form x to the power, I don't know, k, well, respectively, x to the power L. So they have no constant coefficient modulo 2. So the constant coefficient of both q bar and r bar is even. And this means the constant coefficient of x to the power 100 minus 2 must be divisible by 4. And this is not the case. So the general formulation of Eisenstein criterion is as follows. In general, if you have a polynomial with integral coefficients, so p is an x to the power n plus an minus 1 x to the power n minus 1 plus and so on plus a0. And there exists p prime such that p does not divide an. P divides all ai except an, and p square does not divide a0, then this p is irreducible. And the proof is exactly the same. And to conclude, I would like to say that both facts are valid, replacing z by some unique factorization domain R and replacing Q by its fraction field. So I think this is a good point to finish the first lecture.